So welcome everyone to TCS Jagan seminar. So this week we have Paul Bastide, who is visiting us for 2 weeks actually, and he's coming from Oxford, where he's doing his postdoc now, and he was doing before his PhD in Bordeaux and in Delft, and he will talk this week about universal posets.
Okay, thanks Clément for the introduction. Thanks a lot for the invitation to give this talk. So I've been a bit unfair actually in the end. I hesitated a bit of how much content I would end to put in the presentation, and depending on how it goes, how many questions you have, we'll see how much we'll cover. It's not important that we cover everything, and I don't want it to be too heavy either. So it also means that please feel free to ask questions at any point if something isn't clear. It also means that even if you're lost at some point, you could come back to the talk and enjoy another problem, which is kind of nice. And it's also means that I've been unfair to my co-authors because here I only put 2 of them, but I might talk about another set of results, and I'll cite my other author later. But the first part, at least, of the talk would be with a joint work with Carla Groenland, who is in Delft, who was my supervisor, and Rajko Nenadov, which is now in Auckland. Great. So let's a bit define the terms in the title first. So a universal object is a very broad concept, actually, in combinatorics. It's just morally the idea that you have some class of object, combinatorial object, and you would like one member of this class to represent everything that is in this class, to contain everything that is in the class. So if we talk about graph, what we would like is one graph that contains a class of graph. And the containment relation, you can define it for many different containment relations and have a lot of interesting problems. But for this talk, we'll only consider induced universal graph, at least. I will mention it when it's not induced, and when I say just universal, you can imagine induced. Okay, so here you have an example of a graph on 5 vertices that contains all the graph on 3 vertices. Okay, so you can find, for example, the triangle here, the independent set, edge, and 1 independent vertices and 2 edges. Okay, so you can find all of them as induced subgraphs of this graph. So in this case, I will say that this graph is universal for the class G, which is the graph that's over there. Hope this is clear. Great. So maybe one first result on this universality concept that wasn't stated as such at the time. The word universality was not coined at the time, but it's some result that you might know, which is the existence of the Rajko graph, which is the limit, if you like, infinite graph, which is the countable limit of G and P for P equals 1/2. So if you didn't understand this, I will give you an idea of what I mean by that. Let's say you have some kind of infinite process where you construct larger and larger graphs. So at the beginning, you have a graph of size 1 with just 1 vertex. Then you create a graph of size 2 by adding a vertex and adding this edge that I draw here with probability 1/2. Okay. Now you add another vertex, and then you add each edge to the previous vertices with probability 1/2, and you continue this process forever. Okay. Then the limit of this process, the infinite graph that you will obtain, you can actually show, and this is the theorem that is above, 2 things. That first, it's unique, actually. You can always find the isomorphism between the 2. So it's a unique limit, and it contains all infinite graph. And to see that it contains all infinite graph, it's actually quite easy. You do somehow the same process. First, you involve you embed the first vertex somewhere, like for example, add the first vertex, and then you embed its neighborhood, and etc., etc. And it gets a bit more tricky, but this is the main idea. So this is a universal graph for the class of all infinite countable graphs. Okay, this Rajko graph. And because here we like poset, I also like poset, we can ask the same question about poset. Does it exist a countable poset that contains all countable posets? Okay. And this actually has been answered too. Such a poset also exists. And maybe interestingly, so Ackermann was way before his time, but for example, Erdős and Renyi and Rado reinvestigated this Rajko graph in the 60s. But actually this poset, a universal poset, was of interest even before that. So somehow they were more interested about the existence of universal posets somehow than about the universal graph statement. And this is due to some interest in model theory and category theory about those universal elements. I cannot say much about this relationship, but yeah, just to tell you that some other part of math are actually interested with this kind of question. Right. Okay, so that's what I said. And why, in general, you would like to construct those universal objects outside of model theory and category theory could also be for two things, mainly. Either you have some kind of proof that is nice under induced containment. So if you want to prove some property for a class of graph, but it's tedious to prove it for every graph, and it happens that your proof method is very nice under subgraph, induced subgraph, for example. Yeah.
And since a Rajko graph is unique,
yes,
there is maybe a deterministic way to construct it.
That's a good question. I would think yes. I would not be able to state in a natural, simple way, but I know that.
Okay.
Yeah, I don't know.
It should be known, I think.
Yes, I think.
Remember this, but I don't remember
I don't remember the construction either, but I would think my intuition tells me yes, but I would not be able to tell you exactly why. Yeah. So what I was saying is, if you have a proof method that's working on one graph, but it's a bit tedious, you don't want to prove it for every element of your graph independently. What you could do is actually take a universal object, prove it just on the universal object, and sometimes it simplifies, or just make some proof possible that were not possible before, just through this method. And in computer science, sometimes you have some property that you want to compute on all graph in some classes in order to solve your problem. Often happens in some game theory problems. Then if you have a small universal element to the class of graphs you want to compute, let's say your polynomial size compared to the element in your set, then just computing it to this unique element sometimes is already solving the problem. So this allows some nice computer science insight. Great. Okay, so all that I said, that I talked about for now is the infinite version. But we can also talk about finite graph. So what if I have just a set of n vertex graph? What can I say? What's the size of the smallest universal graph that contains all of them? This is something that has been investigated just after they find this Rajko graph. And the first bound was of size k to the k over 2, which was then improved by Allen by some very nice argument that's very precise, like up to even not a constant, but really a little O of 1 in the size. We know exactly the size of the smallest graph that contains all n verticals, which is a beautiful proof going through some kind of modification of G and P for a nice value of P and a nice value of N. Yeah. Okay. One more remark, one thing that I will use multiple times in the talk, I will talk about it later again, is that you can always, if I give you a family of graphs, you can always give a lower bound of what would be the best size of a universal graph you can find. And that's just counting how many graphs I can find in this object of some size. So if I have a graph of U of some size, and I want to find n vertex graph inside this graph U, well, the best thing I can do is for any n choice of vertices in my graph U, I have this unique graph in my family that is defined by this. This is the best. Okay. So in particular, in size of U, which is n, is always larger than the size of my family. Okay. So that will give you some lower bound on yeah, what's the best we can do. And if you look here, those lower bound are height for all graphs. The number of graphs in total is indeed of the order 2 to the n squared divided by 2, which is actually satisfying the equality up to this little thing here, this statement here. Okay. Yeah, so this is what I wrote here. Okay, great. So again, same thing. We talked about infinite graph, then infinite posets, then finite graph. What about finite poset? And this one, surprisingly, has not been, we're still far away from understanding this completely. on one side, we have this trivial lower bound, let's say, that gives you that it's at most n over 4, just because you have 2 to the n squared over 4 posets. But on the other side, the only universal poset that we know is the hypercube. I'll explain why it's universal a bit later, but the size of the hypercube is 2 to the n. So on one side we have 2 to the n over 4, and on the other we have 2 to the n. So there's still an exponential gap between the two. Yes. And this has been studied for multiple reasons. One reason is go through graph again. So the comparability graph of a poset is just the graph you obtain when you put an edge between any comparable element. Okay. Then what was proved quite recently, a few years ago, was that there is a graph of optimal size that contains all comparability graphs. Okay, that's a beautiful result. They prove a bit more than that in this paper, but yeah, okay. One conclusion and the main goal they were after at the beginning, before proving an even nicer theorem, was to solve this question and try to get the smallest universal graph for the class of comparability graph. So they found it. It's roughly optimal because, as we saw, it's 2 to the n over 4. But then they thought at first that the graph they obtained was a comparability graph. So somehow that it implied in particular that if I just look at the graph, I find a good order in this graph, it gives me the comparability graph of a poset. I look at the poset. So I have a universal poset that contains all posets because, yeah, I have a universal graph that contains all comparability graphs. But it's more subtle than that, because the graph itself that they construct is not a comparative graph at all, actually. So you cannot make it into a poset. So they asked the question, what can we do for poset? Or what can we do even just for comparability graph itself? That's another question. Yeah, can we do better than this n 2 to the n? And yeah, can we reach this 2 to the n over 4, for example? Okay. So that leaves us with multiple questions. Okay. From the hardest to the easiest, probably. Okay. So first of all, we could ask what's the size of a poset that contains all n-element posets, the minimal size, or we could relax it a bit and ask for, did I write the same thing? Okay, I write the same thing multiple times. This one should be, what's the size of a comparability graph? I'm confused. Oh no, yeah, sorry. This one, okay, sorry, my bad. The first question should be, what if we want our poset U to be inside the hypercube? So I restrict my smallest element, my universal poset, to be a subset of the hypercube, because we know the hypercube is universal, so we can ask, is it optimal for this relation? Or can we find something way smaller inside the hypercube itself that is also universal? So here it should be U inside the hypercube. Here it's asking for any poset. You can find it in the wild. It doesn't need to be in the hypercube. And here it's asking just for comparability graphs. So you don't need to be a poset. Okay. Enough talked about this. So as we saw, we have a lower bound of 2 to the n over 4 for all of them. And this comes from this counting argument of just counting the number of posets. On the other side, we have the Boolean lattice. So let me tell you about how you prove that the Boolean lattice is a universal poset. One way you can do that is you denote your element 1 up to n in your poset with any order. So maybe let's try to do that here. Let's draw one poset. I don't know which poset you like. I'll try to do an arbitrary poset. So you take your favorite poset on n element, okay? And you'll name the vertices 1, 2, 3, 4. This is arbitrary. I could have chosen any kind of things starter. Okay. Now what you do is I want to define set in 1 up to 4 such that this poset is an induced version in the hypercube. Okay? So what I will do is for any element, its image will be the set of elements that is below its im in the poset. So for example, this element It's a minimal element, so it will be associated to just the set containing its own name. This element, it's below itself, of course, and it's also below 1. So the set associated to this element will be 1, 2. The set associated to this element will be 1, 3. And the set associated to this element will be 1, 2, 3, 4. It's below everything, okay? And yeah, you can see two things. It's very easy to now see that any element is indeed, any element that is below in the poset is also included in the set I defined, and that all this function is really mapping all my element in the poset to a subset of 1n, right? Because I only have at most n names, okay? So this is one way, deterministic way, if I give you a poset, to find an embedding in the hypercube. In particular, if you look at incomparable relation, they are maintained because each element contains its own name. So if two things are incomparable, in particular, they contain their own name in their image, but the other one does not contain the name 3. Okay. So this is one way to do it. There are slightly different ways to embed a poset in the hypercube, but this is the main canonical way. And I will say that this is what I call a simple embedding. If I find an order of my vertices so that I can do this deterministic mapping in the hypercube, this is what I call a simple embedding. Okay? Good. What we prove with Carla and Rajko is that actually you can improve that by exponential factor, and even if you stay in the hypercube. So what we prove is that actually there is a subposet of the Boolean lattice that has only size 2 to the 2n over 3 instead of 2 to the 2n, which already contains all element poset. Which is kind of surprising, because somehow the hypercube is so studied for many reasons, and so symmetric somehow, that a lot of people that we talked to before getting this result could have guessed, and ourselves maybe included, that the hypercube was somehow optimal in some sense, at least minimal. Right. Okay. So let me tell you about how you go to prove such a thing. We actually split the theorems into two lemmas. First, you would like to find the posets in which you can embed posets that have long antichains. And on the other side, you would like to find the universal poset on which you can embed posets that have small chain decomposition. Okay? And by deal worse, you always have one of the two. Either you have an antichain to side n over 3, or you have a chain decomposition in at most n over 3 chains. Okay? So basically, your final universal poset will be the union of those two, and you will cover everything. Okay? Is it clear? Yeah. And one interesting thing is that actually, if you look at posets that have antichains of size, big antichains of size A, it's not only that you can find a smaller subset of the hypercube in which you can contain them, but it's really that there is a sub-hypercube, hypercube of lower dimension that contains them, which is even stronger. Okay, so let's see how we go to prove this. Okay, so I re-put on this slide the thing I explained just before about how you can embed poset in the hypercube. Okay, so your first idea maybe, at least our first idea was, okay, perhaps because there is so many naming, right? I could choose whatever name I want for my vertices. So there is n factorial choice of this simple embedding. Actually. Okay. Perhaps if you make a smart choice for every poset, you will manage to get small numbers of sets in total in the hypercube that are used. Okay. Sadly, this is false. So we can prove that whatever, even if you make the smartest choice for this simple embedding, then you will end up still using most of your hypercube. So you need to do something different, okay? But it's not completely useless. It's even useful, because I will still use that in the case where I have a small chain decomposition. So when I have, you have to imagine in your mind that you have roughly n over 3 chains, and they are all kind of long. Actually, long will be just size 3 will be enough for the computation, but for your mind, you should just imagine that you have very long constant size chains in your poset. Okay? And what I want to prove is that if I have such poset, so maybe let me draw something that looks like one of these. So there are some long chains. Okay, and you would like to find the numbering of those chains so that some set in the hypercube, quite a lot of set in the hypercube are not used into any into your embedding, right? And in any version of your process. Okay. So this is my chain decomposition. Of course, I could have very complex behavior between the chains, and I will talk about that later. But for now, let's choose a very simple numbering, which is natural. I look at my first chain, and I number it 1 up to k. Okay, this sucks. Okay, and I will do that for all the chains. Actually, I will start at k plus 1, and then 2k, etc., or something. And I will show you that now, just by doing that on one chain, I'm already gaining something. Okay, so now I can look at someone else in my poset, maybe this element. Okay, and how can he interact with the chain? What kind of comparability can he have with the chain? Because this is a chain, actually the comparability to it is very structured. There is a set of elements. Let's say I want to know about the things that are above this element in the chain. Okay, so there is a first element that is above, and then all the other elements need to be above just by transitivity. Okay, so actually, if I look at every set of above comparability, okay, I just want above cover, not cover, sorry, comparability, then they always look like intervals, actually, intervals that goes up to k. So actually, how many choices there are? There are just number of choices from 1 up to k. So there is a k possible set. It's, well, I guess k plus 1. It's either the empty set, set that contain 1, set that contain 1, 2, 1. Okay. And I'm already gaining quite a lot. It's quite fewer sets than if I had no structure on my chain. If I had no structure, I would have all the subset of 1 to k. I would have 2 to the k possible set. To the k possible set. Okay. So in particular, if you imagine that my poset can be partitioned into this long chain, for each chain I'm using only k possible set instead of 2 to the k. So when k grows, this means that the number of sets in my hypercube that I'm using is shrinking quite a lot, and it's shrinking indeed by some exponential fight curve between the two. Okay. So that's the way you do that when you have long chains. I hope I managed to convince you of the rough idea. I didn't give you all the proof, of course. Okay. So that's what's written here. If I want to do the computation, the number of possible, if I have some chain decomposition and the ith chains of size ci, the number of possible sets is the product of ci plus 1, the plus 1 coming from this empty set. Okay? And if you know that your number of chains is bounded, that if it's too large, I will handle it with the empty chain case. So I can say, let's suppose it's bounded by n over 3. Then you can try to optimize on this function. So maximize this function when you know that I is going from 1 to n over 3. Because it's a convex function, the worst case is actually when all the chains are size 3, what you get is 1 plus 3, so 4 to the n over 3, which is indeed 2 to the 2n of 3. Okay, 4 to the n over 3, which is ci plus 1, equal to the 2n of 3. Okay, it's okay if you don't get this computation, it's not important, I'm just making it a bit more formal. Okay. In order to do all this computation, I somehow subtly supposed that I knew my chain decomposition. I knew which chain at which size. Okay, and this is something I can do because this partition, I can guess it. I just fix the partition, there is at most exponential square root n of them. This is a well-known result. So it's a small order term. I can just take a union of all the universal posets I will find for a fixed partition. So yeah, it'll get a small order term, and then you indeed get the 2 to the 2/3 times n. Okay, great. Now let's see what we can do for the anti-chain. So somehow we saw that
Why do you need that every chain is large? Is it something that you need in order to make this computation? What breaks it?
No. It's fine if some chains are small. When do I say that all my chains are large? Is because this function here, which is the key point, is convex. So it will be maximized when all the chains are the same size. But what it means is the worst case is all the chains are size 3. If you want to take plenty of chains of size 4 and then chains of size 2, I'm also fine. And this will be one member of my partition. It's just that the product will be less than this. So whatever is my partition, I will always bound it by the worst case, which is 2 to the 2/3. Yeah, and you cannot really do better because this is really the leading factor. Does that answer your question roughly? Okay, so now what can we say about anti-chains? Maybe I won't go into too much details, but one thing that we can see first is that this kind of miracle cannot work anymore because we proved that for all posets we cannot do it. We cannot find this simple embedding for all posets. So in this case, we'll need to use a different embedding, okay? And what we will do is we'll look at the anti-chain will be called A. We have the elements that are below the anti-chains, so it's all the elements that have either no relation to the anti-chains or are below at least one element of the anti-chains, and the things that are above. This is indeed a partition of your poset into 3 sets, okay? And in particular, you know that if something is below A, then it will never be above someone that is above A, okay? Let's just break your transitivity property. Okay. The intuition in this case will be that instead of giving one name for each element of my poset, what I was doing in the simple embedding, I would like to compress the names when the elements are in the anti-chain. Okay, I would like to use less elements to talk about elements of my poset that are in the anti-chain. Okay, so you don't have to look so much at the numbers here, but what I can do is instead of associated to every element of the anti-chain one element, I will associate it to one subset of a set of size 2 log A, just to have enough space to have enough subset, okay? And what happened is, then I'm using way less element in my hypercube. I'm using size of the things that are below plus size of the things that are above plus log of the size of the thing that is in the middle. And you have to imagine that the thing in the middle is like n over 3. Okay, so I'm using 2 to the n over 3 plus some small log of n. Okay, in terms of current set I'm using. Okay, and it happens that somehow you can play on this simple embedding and change it slightly. It's quite subtle in some sense, like it's easy to break. But if you do roughly what you were doing for simple embedding for the things that are below, and you do some kind of symmetric things for the things that are above, then everything will be fine, okay? And for those that know about labeling scheme, which I often use for universal structure, what happens is the elements that are both below and above, they are not remembering the adjacency to the elements that are in the anti-chains. Actually, the elements that are in the anti-chains are remembering both who is above and who is below them, okay? And since they don't have to remember anything for the rest of the anti-chains, they gain n over 3, okay? That's roughly the idea. And below and above gain n over 3 because they completely forget about the anti-chains too. So it's somehow sum up to n over 3 too. Okay, good. Now for those that were starting to get lost, I hope not too many of them, you can come back and I will talk about another subject with way more pictures. so I hope it will be a bit easier to follow. Yeah, and I'm happy to get any question on what's before.
Can you show back the previous slides, please?
Yes. Yes. So I can go into the details, but this is the exact definition of the image. So this is exactly like before for the simple embedding, for the things that were below. The things that are in the middle, they both remembering who is below them in the set that is below, and who is, how is it, is done as the opposite? Yeah, who is not above them. Okay. And Z is containing all the elements in the string set of the anti-chain. So let's say that this interval I, for which I have one set of the anti-chain. Okay. And it's, remember, everything that is not above them and everything that is below in...
What is this Li encoding?
This Li is just an arbitrary subset of size log A of this interval I. Okay. And roughly you have to think about it as the name of my element in the anti-chain. Before in sample embedding, I was given one name from 1 up to n to each element. Now elements that are below and above still stay the same, but elements that are in the anti-chain, they get a name which is like the set 1, 2, 3, 4, for example.
Okay. The Li is unique for each different element
yes.
of A. That's what we need.
Yes. Sorry. Oh yeah, I forgot to write it here. So Li is just a unique set of this subset of size log A. Okay. This is some set of integer that is not used as a name for xi. It's not used as a name for z. So I can use any subset of this to name my anti-chains element. Okay. So in particular, I use subsets that are both all of size log A. This way, they are all incomparable. This makes that these sets, just because Li is there, will never be comparable. And yeah, those images are always incomparable in the hypercube. And in particular, Z will contain this I is the union of the Li, for example. So yeah, this is the idea that in worst case, they contain all the Li, all the names of the elements in the anti-chain, because the anti-chain itself is remembering who is not above it by containing the J of the things that are above.
Okay, now I get it.
Okay. It's a good question. Yeah, it's both simple if you sit down and think about it, but at the same time, it's a bit hard to see all the subtlety like you point them out nicely. I hope it's a bit clear. Okay, so let's go in another topic that I quite like. So we saw that it's known to find a graph that contains all comparability graphs of a poset. And it's known, it's harder if you want the graph to actually induce a poset. If you want a poset to represent a poset, it's harder. Okay. So a very general question would be, even for graph, if I want the graph that represents my class to share some property of the class, what can I say now? And this is why we define in a very, the idea of faithfulness. Okay. So for an infinite class F, infinite, yeah, okay. It's a class of finite graph, okay, but it's infinite, such that let's call Fn the subset of this graph that has exactly n vertices, okay. Then the universal graph U for Fn is faithful if it's also in F, okay. So like this, it could be weird, but you really have to take your favorite class of graph, for example, planar graph, that we'll talk about after. The idea is I want a graph that is both planar and contains all n-vertex planar graph. Okay? And now I can ask the same question. Can I make it small, or what can I say about it? In particular, in another version of not exactly faithfulness, but a bit in the same trend of idea, you can put the product structure theorem for planar graph. It is a universal graph for planar graph that preserves nice structure about planar graph. And we saw that this tool is super useful in order to prove other things on planar graph, structure properties. Okay. So it's faithful in the sense that it keeps property, but it's not planar graph in the end. Okay. So here we're asking for something stronger. Okay. Okay, so what can you say about faithful universal graph for planar graphs? So first, if you're not faithful, this is something that has been studied a lot. There's a series of papers trying to get the smallest one. The current state of the art is n to the 1 plus some epsilon, like little, you have to think little of 1. Okay, so we know how to do it quite small. Okay, it's almost the same size as the graph it needs to contain. Okay, and you have a trivial upper bound on being faithful because being planar is kept by disjoint union. Okay, so if I take just the union of all planar graph, this is a faithful universal planar graph. Right, it's still planar, and this has size n to the 28 to the n. So this bound is just obtained by saying every graph has size n, and this is the number of planar graph on n vertices, or an upper bound on it. Okay, so we are between this polynomial function and this constant to the n. Okay, and the idea is, can we make way smaller than this? Can we somehow get close to this bound? Okay, and this traced back somehow to a question from Ulan in the 60, 70, I think, where he asked the same question in the infinite case. So do you have a countable planar graph that contains every countable planar graph as in this subgraph? Okay, and Pach answer in 81, that's no, it's not the case. Actually, if such a graph contains all planar graph, then it needs to contain a K5 minor. Okay, and Pach asked this question about faithfulness already. About, okay, it cannot be planar, but how close can it be to be planar? So it's more in the discussion, he didn't ask any specific question about the property he wanted to keep, but really asked like, okay, I could not make it K5 minor 3, but can you make it something that keeps property of planar graphs? And quite a few years later, 40 years later, there was a beautiful paper of Yun Moar, Samar, Thomassen, and Wood that proved that the answer is still no. It cannot be close to planar graph in some sense, in the following sense, which is it actually not only contains a K5 minor, it contains a K infinity minor. Okay, that's scary. But yeah, for people that likes minor theory, this is how far you can be from planar graph, I guess. Right, so this is for the infinite case. And it's natural to ask, what can we say about planar and finite now? Okay. So here we have the counterpart of countable versus incountable. For the finite version, now we know that everything is finite. We saw that we can do C to the n. So the counterpart is polynomial or exponential. Okay, can you make it polynomial and still planar? Yes.
Is it easy if you replace induced by subgraph?
It's not easy.
It's also open, or
you mean this result?
Yeah, this question. Do you ask it really for induced?
I don't want to state something that is not based in the theorem, but I think it would work for non-induced. For this result, it holds for non-induced.
There's a positive question for the answer to Ulan's problem?
No. It's the same answer for non-induced.
It's no and no?
Yeah, it's no and no. Yeah. I'm 90% sure for this. Okay, so in the case of the induced design, for sure, there was a recent development, and they managed to prove that indeed, if your planar graph, roughly similar to what happened in the infinite case, you still need to be of the size 2 to the very small polynomial. Okay, so you cannot get something that is polynomial. Okay. And planar. Okay. And what we answer to is this follow-up question of Pach. Can you get close to polynomial in this finite case? Okay, which took quite some time to answer in the infinite case, and it was a bit quicker in the finite case. And what we managed to prove is actually strengthenings both in the quantitative sense and qualitative sense. We proved that for any t, any fixed constant t, you cannot hope your graph to be kt minor 3, so this is the equivalent of this k infinity, okay? But we are working with finite graph here. And the size is now 2 to the cn, okay? So it's optimal up to this constant C. Okay, so it's really, you have to think of it of, it's really hard to do way better than taking the stupid disjoint union of your graph if you want to stay KT minor free. Okay, good. How much time? Okay, so I can tell you a bit about the proof. So,
could you show again just the last?
Yes, of course. It's a good idea to leave so that the results sink in a bit. Okay. So I'll repeat it one more time. What we are saying is, suppose you have a graph that's both KT minor free and contains all planar graph, then it needs to be of exponential size. Okay. Okay. Let's see what we can say about this and how we go with the proof. So the first thing you want to extract is a tame family of planar graph. We'll see in one sense I mean tame, but just to make the proof work somehow. You want to be able to say something about your family. Okay, so let's look at grids. Grids are nice, and triangulated grids are even nicer, okay, because somehow they are critical in the sense that if you add too many other edges in a triangulated grid, okay, you will end up very fast creating KT minors. Okay, I will give a statement of this, end wavy thing in the future. Okay, but let's suppose for now that we are interested with those objects. It's nice; they are somehow critical, but we also need to have a lot of them because we want to find them in a small universal graph and manage to say some contradiction. Okay, because of course by themselves they are fine. Okay, so let's try to count them. Well, maybe take a guess. How many triangulated grid do you think there is of size n that are non-isomorphic to each other? At least n squared? 2 to the n squared? No, not really, right? I mean, it depends. I say n as the total number of vertices, not the size of the grid.
Also the dimension.
Yeah, if both sides are size n, then you have 2 to the n squared. So let's assume that n is the size of my grid, really, the number of vertices. In this case, is 2 to the n, right? It's 2 to the square root n squared. Okay, and that's just, you say, for example, one way to count it very easily is you annote which direction you put this diagonal edges. This gives you a word on an alphabet of size 2, and the word is roughly size n. Okay, we'll have something like size n of 2. Okay. For any 4 vertices, for any square, you have a word. Okay. Now you still have some symmetry because you could turn it in 4 different directions. You could remove one of the edge to break the symmetry, and you get exactly what we said before, that you have exponentially many. Okay, so you're happy. What this won't mean is somehow you hope that because we have so many of them, and you are supposed by contradiction that you manage to pack them in a small universal graph that doesn't contain KT minor, then they need to fit into each other a lot. Okay. Okay. Now I'll tell you what I mean by this criticality. And it's really close to the idea I was saying about, which is if I add t to the 10 edges that were not present in my triangulated grid and that are disjoint, so you have to think about the matching, then my graph will contain a KT minor. Okay, this is not completely true. There is a subpart which makes the paper a bit longer and more technical. That if those edges are too close to the border of your grid, actually you cannot do this. You have to imagine that the edges are inside your grid, not just on the border. Otherwise, you can create actually vortices and stuff like this for those that know about minor theory. Okay, but it's still quite kind of nice. Like just for a function of t more edges, I can get KT minus. Right. So now the idea would be I take one of those grids such that a lot of other grids are intersecting it in very different way. Okay, and I will use the other grids in order to contract some vertices that are not in the image of my grid into those jumps edges. Okay, if I manage to do that a lot and get a lot of those edges that are also at the interior, but let's forget about this interior film for now, then I will get my KT minor. Okay, so now let's first see what I mean by a lot of them are above each other, because this is intuitively true, but you need a formal statement. So let's suppose U is my universal graph, and I have some image of my grid somewhere. This is the set of points of my universal graph. It's a kind of an abstract picture. But yeah, okay, I can look at this, for any image of a triangulated grid, I can look at which vertex set of U is used by this image, right? So that gives me a subset of vertices in U. Okay, so for each graph, planar graph, I get a set of vertices in U, subset of vertices in U. So in particular, what I have is a family of set on the ground set vertices of U, okay? And this family is of exponential size. By Sauer-Scholler lemma, it means that this VC dimension is high. So for those that don't know about VC dimension or Sauer-Scholler lemma, you have just to trust me that it means in particular that there is some set S for which I have both one grid that contains all the set S, that's using every element in the set S, and for any subset of S, I have a grid that uses exactly those elements. Okay? So let's consider the grid that contains all of them. Okay? So that's something like this. You have to imagine that the element of S has those mint element, mint colored vertices, and the other black element are anything in my graph U. Okay? In particular, because there are nice grids, I remove the diagonal edges, but you have to suppose that they are here. It's just that they are not important for the proof, for this part of the proof. In particular, I can find two paths that cover all my vertices and that are induced. So here you have one in orange, but if you move it just one to the side, you have another one. Okay? One of them, by pi-general principle, will see a lot of elements of S. Okay? So in particular, let's suppose that this orange one sees a lot of elements of S. Okay? Then I will annotate my element. Okay. Yeah. I will annotate my element of S 1, 2, 3, 4, 1, 2, sorry, 1, 2, 3, 1, 2, 3, 1, 2, 3, according to their order on the path. Okay? And now let's split S into two sets. There is the mint set and the purple set. Okay? Now, because I'm shattered, and what I said just before, I can look at the graph which intersects this grid on the mint vertices, for sure, on the purple vertices, not at all, and on the black vertices, I don't know. Okay? So it's a grid that will contain all the mint vertices, none of the purple, and some of the black maybe. Okay? So this is my graph H, some other grid. Okay? And now I want to do some kind of trade-off. I will say, I will look at those mint and purple elements, and either I will manage to contract a subpath of this long orange path into a jump in H, or I will manage to find something to contract in H that will create a jump in G. Okay? So let's look at one lucky case, maybe. I look at the elements of those elements, the image of those element 1, 3 in the other grid. So maybe they are over there. So there are already an edge between them. Okay? In this case, it means that I have this jump. It is in my universal graph. So I created one jump. Okay? It could be that they are very far away. Okay? But if they are very far away, in particular, there is a subpath between 1 and 3. So maybe this black vertices is also in graph H, which is not a big problem. I just start from vertices 2. Vertices 2 and 3 are linked together, and some vertices is before in graph H, and this will create some jump in H. Okay? So imagine for now that this vertices is not in H, this black vertices. Then by contracting the path from 1 to 3, I will instead create a jump in H. Okay? And this imagine that the black vertices is not in H is actually not a real problem. You can just always move this set S, this min vertices down if the vertices here is also in both, because this is the property of the min vertices, they are in both grids. So it happened that this vertices is also in both grids, then I'm happy. Okay? So what I said is I split my set S into subset of size 3, and for each subset of size 3, I will manage to create either an edge in this in graph H or a jump in graph G. Okay, since my set of graph was so big that my PC dimension was super big, my set S is also big. I created a lot of jumps. I used my lemma about triangulated grid being critical to prove that it contains a KT minor, and I'm done. Okay. So this is how you use some kind of structure of your universal graph to prove that it cannot be so small. Okay. So this is the final drawing of what I get. I get some graph G, some jumps both in H or in G or in H. I just look at the graph that contains the most jump, contains a lot of jumps. I'm happy. Okay. Now I'll conclude with some nice question about this. But if you have any question about this proof or anything else, please feel free to ask them. Okay. So to conclude, just some very nice natural question. We still don't know what's the size of this smallest universal poset I was talking about at the beginning. We improve it from 2 to the n to 2/3 n, okay, but still the lower bound is still n over 4. So there's still a huge gap between the lower bound and the current bound that we know. Okay, so I'm quite curious about this. That's actually something we're working on with Yenji and Julia. We believe we can improve this 2/3 by a tiny bit, but not a significant amount yet. And we're trying to work towards something. Okay. Another problem, I didn't mention it here, but this universal, this faithful property, you can ask it for a graph parameter. So for example, if you have all the graph of true width k, you can ask, is there a universal graph of true width k that contains all of them? And is it small? Okay? Okay, so there is a small condition missing in this question. And we happen to prove something in this paper about planar graph. We also prove interesting things about true widths, path widths, bounded degree, stuff like this for those parameters. But one thing that we managed to do for true widths but didn't manage to do for path widths is find a universal graph that has path width c times k that contains all graph of path width k. So you want a linear dependence in the path width of your universal element compared to the class of graph.
Just to be clear, for true width, you could do this.
For true width, you can do this with a very small constant, 2, I think, or 3 times true width, maybe 3, I think. You cannot do it. You cannot have. Why did we add this constant factor? Is because if you look at a graph of true width k and ask it to contain all graph of true width k, then now you have exponential bounds. Now we can prove that this is impossible. So you need somehow to add a tiny bit to the true width. You cannot just have the same true width. But it could be, for what we know, that you can actually do an additive constant even. It could be that between, you have a universal graph of true width k plus 10 that contains all graph of true width k. Even k plus 3, we don't know how to separate them. And in particular for path widths, what we know here is k squared. We know how to do by taking the square of the path width, but we don't know how to do linearly, even though for true widths we have this linear. So there is somehow a different behavior that probably comes from the fact that we don't know how to construct the universal graph for it. Some of my quarter at some point were believe that there is something deeper there, and it's actually not possible. I don't know what's their current statement, so I shouldn't tell. But yeah, I think it's interesting to understand this question. And yeah, I think this is very general. We looked at it for planar graph, tree widths, path widths, because that's the most general and studied classes of graph, but you can choose your favorite class of graph and see if it admits the faithful universal graph. And okay, one interesting direction would be dense graph, for example, because planar, tree widths, path widths, bounded degree are very sparse graph. And I wondered if you take click widths, twin widths, or this kind of stuff, is it still true that you have nicely sized graph that contains all of them while keeping the path widths, twin widths small? Okay, and I will stop on this. Thank you a lot.